Good evening, everyone. I'm Anish Ambikar, PhD candidate from ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course, Computational Mathematics with SageMath. So, in this week, we learned different methods to solve linear programming problems, specifically the revised simplex method, big N method, two-phase method, and using duality. So, with that in mind, we have a few examples which will be going through which we'll be going through the concepts taught in this particular week. So the first example one asks us to maximize the objective function 19x1 plus 13x2 plus 12x3 plus 7x4 subject to a series of constraints. So three inequality constraints are given. Following positive one non-negative constraint applied to each variable x1, x2, x3, and x4. So to solve this, we'll be first using going through the simplex method itself. So firstly, we specify our A matrix, which contains the coefficients of all the constraints. We also specify vectors B and C, which correspond to the right hand side of the constraints as well as coefficients of the objective function. And then we define our interactive using the interactive LPP problem module, we define our problem based on maximizing the constraint. If we show it in the standard form, we can see that like we can see how our problem is defined. So this matches with whatever we have been asked to do. The easiest method to tackle such a problem would be using the simplex method, which we have already seen in the previous classes. So uh, we first to do so, we first need to identify whether certain slack or surplus variables are required. So because all three constraints are less or equal to, we need to add slack variables to convert them into equalities. Then we move around the variables to have the slack variables on the left hand side, and we go through, we write down our objective function and then see along which direction we'll quickly reach our optimal solution. So that is determined by the highest positive coefficient of the objective function. So that is x1 in this case. And from that we look at which is the uh, for the x1 coefficient, we figure out uh, what's secondary variable will exit out of. So in this case, this algorithm runs it through entering through x5 and leaving through x1 and leaving through x5. So that basically rearranges the first equation, and wherever x1 occurs, we just plug in this identity into both the equations. Second, we do the same thing for the next variable. So that is x2 in the objective function. We look at it, and again this particular algorithm rearranges it to rearranges the equations so that we have x2 in terms of, sorry, we rearrange the first equation of x2 in terms of all the other variables and then plug it into our all objective function as well as the constraints. Same process we repeat for the third variable, which is x3, and again finally through x4. So by doing so, we essentially end up with an objective function which is a positive coefficient minus some minus a linear combination of non-negative variables. This basically makes the coefficient as the optimal solution, and all the remaining variables going to 0 will help us achieve that optimal solution. So in this case, x5, x2, x6, x7 all going to 0 becomes our optimal solution, which plugged in gives x1, x3, x4 values. So this is the basic simplex method that we have seen previously, and an iteration of the same using inbuilt functions in SageMath. To use the revised simplex method, we first create an augmented matrix based on the basis set. So 3 by 3 basis one. This is the I cube for the basis set, and then an being the matrix of non-basic columns of the uh, coefficient matrix A, from which we basically from this what we are able to do is basically obtain a feasible solution. From this, we calculate our reduced coefficient, reduced cost, current reduced cost coefficient with respect to our non-basic variables in the form of C minus Y transpose AN, C transpose N minus Y transpose AN. And if this R transpose or our current reduced cost coefficient is positive, then the current feasible solution is optimal. If not, we keep on iterating. If it is not so, then we find out the index q where r value or rq is less than 0. It is the most negative, and then compute yq based on the inverse of aq. And during this process, if we find that y values are negative for all the indices, then the problem might be unbounded. Otherwise, we just follow the process. So here in this case, we have this as my current reduced cost coefficient R transpose row vector, and with this in mind, x1 has the highest positive coefficient, so we enter through x1 and leave out through another non-basic variable which is x5. Rearrange, again find the B matrices B inverse B matrices, again calculate the cost coefficient. Similarly, we go through x2, x3, and finally again till x1 till we are x1, x4 till we are left with a solution where this R is entirely negative. Once this happens, we have arrived at our optimal solution. So in this case, the optimal solution is again 1827, and the values corresponding to it are x1 being 39, x3 being 48, and x4 being 30. So that is one another way to solve this problem. A third way could be directly using the mixed integer linear program problem. Again, an inbuilt function in Sage, wherein we define an objective function based on a vector. We restrict the vector to be non-negative, add our constraints, and if I show the problem, I basically get the same and same objective function constraints and variable value range, from which we find the optimal solution by doing p dot solve and get the values based on p dot get values. So all three methods, same solution. The idea here is to just compare them and see how they uh, how they work. That's it. Uh, since there are no doubts here, we'll move on to the next problem. We have to maximize an objective function given as 2x1 plus 3x2 subject to the constraints given below. 2x1 plus 3x2 less or equal to 30, x1 plus 2x2 greater or equal to 10, and x1, x2 greater or equal to 0. So how do we solve this? We first write down uh, uh, our constraint matrix A, right hand side of the constraint B, and coefficient for the objective function C. We next define an interactive LPP problem and write it down in its standard form. So this is how it looks like. Okay. So I've already taken care of the right, sorry, second equation, multiplied it by -1 so that everything becomes in this form. Run the revised simplex algorithm. So you can see that we have here, sorry, you can see here that the basis matrix B can be written as 1001 standard basis matrix, whereas the non-basis matrix is the AN can be written as like this. The the basic variables would be basically x3 and x4, which would convert these inequalities into equality, whereas our non-basic variables are x1 and x2. And the objective function has coefficients in terms of the non-basic, non-zero coefficients corresponding to the non-basic variables. So, with that in mind, sorry, uh, with that in mind, we run the revised simplex method. So, using my, sorry, so x1, x2, x4, I'll initially form my xn. Xn is given by x1, x2, x4. My new basis, my new basis matrix is given by E inverse B old inverse, and if I my B old inverse is like this, it's already written here, and E inverse is like this. With this in mind, I get my new B inverse, and from that I obtain my cost coefficient, current reduced cost coefficient, C transpose minus C transpose B inverse AN, and the B inverse AN, C transpose B inverse AN, and that B inverse C transpose B inverse is given by my Y trans. Yeah, I run the simplex. I run the simplex method. So what do I see? I first see my two slack variables, my two slack variables x3 and x4 are written in terms of my. So these are x3 and x4 are my basic variables written in terms of my non-basic variables x1, x2, and my objective function written in the same fashion. I because the initial because the initial dictionary turns out to be invisible, we add this x0 to solve the auxiliary problem in both of my variables, and then I write down my cost function as minus of x0. When I use x0 to exit to enter, I use x0 to enter and x4 to exit. So similarly, I then use enter through x1, leave through x0, and that gets me back to my original problem, which looks like this. And finally, I look at the coefficient z and play around with x4 to determine where to get in and get out. So my z turns out to be 45 minus 3 by 2 x3 minus 5 by 2 x2. The optimal value just turns out to be 45, and the optimal solution is that x3 is equal to x2 is equal to 0, which gives x1 is equal to 15. So the optimal solution turns out to be 15, 0. If I go through the same process using the revised simplex method, wherein we calculate the cost coefficients based on our initial uh, uh, based on my initial basic feasible solution. With that in mind, I enter through x1, getting out through the variable x0, auxiliary variable x0, to get new B inverse value. Same process, I get another value of the cost uh, reduced cost coefficient. So first reduced cost coefficient was mix of positive and negative. Second one is also a mix of positive and negative. So I again go through another variable x4 and exit through x3 to obtain a third cost coefficient value. So my finally current reduced cost coefficient value turns out to be both negative, which means that I have arrived at my most optimal solution, and that happens when x1 is 15 and x2 is 0, or x4 is 5, which is essentially what we also saw in the simplex algorithm. Example number 3 will be minimizing an objective function of the form 9x1 minus 10x2 minus 15x3 subjected to the constraints given below. So we have been given three inequality constraints where left hand side is less or equal to right hand side. From these three, we can create a 3 by 3 matrix for the constraint coefficients, a 3 by 1 vector for the constraint right hand side, and we also have three coefficients for our objective function. Apart from this, our variables x1, x2, x3 are necessarily non-zero, non-negative. So we first write down our constraint coefficient matrix A, our constraint right hand side vector B, objective coefficient C, which we want to. So we have multiplied it with -1 to maximize it, and then I write down my interactive LPP problem. So this is how my problem looks like. All the three variables will require will run the simplex method, but you can see straight away that all the three constraints are inequalities, or left hand side is less or equal to the right hand side. What this tells us is that in all three constraints, we need to add a slack variable to convert it into an equality. So when I run the simplex method, x4, x5, x6 are the slack variables added correspondingly. We move around to bring those basic variables x4, x5, x6 on the left hand side, whereas my non-basic variables x1, x2, x3 stay on the right hand side. I rewrite my objective function. Next, we figure out what is the way to, how do we tackle this. So minus 9x1 means larger x1 value, lower will be our objective, and x2 and 15x3. So here they've chosen 10 x2 as the coefficient, and uh, x2 as the coefficient where we enter the equation, and x5 where we exit it. So basically what this would mean is now we write x2 in terms of all the remaining variables, which is what we do for the second equation, second constraint equation, and then plug that into our original equation. So you can see that my z has become 200 minus negative of 47 by 3x1 minus 10 third of xy plus 5x3. x1, x3 again negative coefficients, we ignore those. We only look now at x3 which has a positive coefficient. So of plus 5, we choose the first equation x4, rearrange the equation to write things in terms of x3, and then plug this back into my original coefficient. So from this what we obtain is basically z is 625 by 3 minus 136 by 9x1 minus 20 by 9x5 minus 5 by 3x4. So this is an optimal solution when x1, x5, x4 are all 0. Plugging those, you get x2 as 55 by 3 and x3 as 5 by 3. So that is how we obtain our solution using the simplex method. Using the reverse simplex method, again we first calculate my basis B, I first calculate my initial basis B, from which I can get my first current basic feasible solution. I also have my AN as my uh, AN as my matrix of the non-basic columns of A, whereas B is the matrix of basic columns of A. And with this in mind, I calculate my cost coefficient, current reduced cost coefficient with respect to the non-basic variables. So the non-basic variables x1, x2, x3 are written here. With respect to these, I calculate my current reduced cost coefficient. So it's minus 9, 10, and 50. So we need all three negative to figure out how to move ahead. So we figure out my next new basis matrix B new using E inverse B old inverse. With that in mind, again we calculate my we enter through x1 exiting through x5, and now we basically get our new reduced cost coefficients C minus Y transpose, C transpose minus Y transpose in terms of my current non-basic variables, which are x1, x3, x5. So this is how it looks like. Only x3 has the positive coefficient, so we need to deal with it. So we enter through x3, leave through x4, my new B inverse of the basis matrix is calculated, and from this I get my sorry, current reduced cost coefficient in this form. So this basically tells me that my cost is my objective function is maximized when x1, x4, and xy are all going to 0. So if I go back to my original equations and plug in x1 as 0, x4 as 0, and xy as 0, from that we get my current values for, sorry, optimal solution values for x2 and x1, x2, x3, which are my original variables to begin with. So it turns out to be 0, 55 by 3, and 5 by 3. So this basically helps me arrive at the optimal solution, and yeah, I think straightforward only. Okay, if there are no doubts here, we move on to the next example. Example number 4. We have been asked to maximize the variable, sorry, maximize the cost z is equal to 3x1 plus 2x2 plus x3, subjected to the constraints given below. 5x1 minus 2x2 plus x3 less or equal to 6. 2x1 minus x2 minus x3 less or equal to 4. 9x1 minus 4x2 minus x3 greater or equal to 15. And x1, x2, x3 are non-negative. Again, sorry. Again, we write down our problem using the interactive LTT problem. So first we write down the coefficients. And this is the other way around. All the three inequalities I've chosen in the solution, at least I've chosen to be less or equal to, meaning all three are converted to equalities using three different slack variables. So we first write down our coefficient matrix for the constraints. Next, we write down the right hand side of the constraints. We also write down coefficient for the objective function. From this, we define our interactive LPP problem, write it down in its standard form, and then basically print it out to show it to, just to check if everything is alright. So this is how it looks like. Next, I'll be again solving it through the same process, first through the simplex method. So when I run the simplex method, I see that slack variables x4, x5, x6 are added to the left hand side of the three equations, three constraint equations. They are rearranged to obtain basically my basic variables x4, x5, x6 in terms of my non-basic variables x1, x2, x3. Then we look at the objective function. Z has a maximum positive coefficient in x1. That could be the fastest way. So we enter through x1 and exit through, we could exit through say x6 because it has the largest negative coefficient. Here the method turns through x4. So entering through x1, leaving through x4. So we have x1, x5, x6 in terms of the other variables. And then Z becomes minus 3 by 5x4 plus 16 by 5x2 plus 2x3. So what happens here is all the constraint equations basically have positive coefficient of x2. That is a problem because when we move around the variables and rewrite this, as well as in the as well as in the coefficient x2. So this problem is basically unbounded in the x2 direction. Like however large we keep on making x2, we will be getting sufficiently large x1, x5, x6 as well as z. So we do not have a solution in this case. If I run the revised simplex method, I expect it to run into the same problem. So firstly, it sees that the reduced cost coefficients are all positive. We need them to be all negative. So it enters through x1, leaves through x4, creates the new B inverse matrix. And again, you see uh, current reduced cost coefficients coming out to be two positive and one negative. Okay, yeah. So here it turns again here also it turns out that the like that the uh, problem is not bounded along x2 direction. Example number 5. Solve the linear programming problem using two-phase method. We have to minimize for x1 plus x2 plus x3 subjected to the two equality constants given below, where each of the individual variables is non-negative. So two-phase method is basically used when when we do not have a basic feasible solution available at hand, and we first have to find a starting basic feasible solution, and after that we use the simplex method. So basically two-phase method we introduce in the phase one, we'll introduce some artificial variables as well as an artificial objective function and find the basic feasible solution with the objective function driven to zero. In the second phase we'll be using that basic feasible solution from the first phase to initialize simplex algorithm to solve the original LP problem. So here we are given a standard LPP in standard form where we have to minimize f is equal to 4x1 plus x2 plus x3 subjected to the two constraints which are 2x1 plus x2 plus 2x3 equal to 4, 3x1 plus 3x2 plus x3 is equal to 3, x1, x2, x3 are all non-negative and the right hand side of the equality constants are also non-negative. Okay, so this is basically of the form f is equal to minimize f is equal to c transpose s subjected to ax equal to b with x greater or equal to 0 and b greater or equal to 0. We now introduce one non-negative artificial variable for each of the equality constraints to create the artificial problem. Minimize z is equal to y1 plus y2. So y1, y2 are my two non-negative artificial variables because we have two equality constraints subject to we basically write instead of ax is equal to b, now we have ax plus y is equal to b with x and y x y b both all being greater or equal to 0. So y1 is added to the first equation, y2 is added to the second equation, and the non-negative condition is written here. This now what we do is we basically move around y1 and y2 on the write y1 y2 in terms of the other variables which are x1 x2 x3 and then write down our original functions the objective function for the artificial problem. So it's 7 minus 5x1 minus 4x2 minus 3x3 subjected to this. Okay, so a lot happening here, but what basically we are doing is instead of uh, ax is equal to b as the constraint, we have ax plus y is equal to b and sum of y going to 0 which will basically mean by I or like each ith component of y going to 0, which should in turn mean that my basic feasible solution for ax equal to b can be obtained indirectly. So it would be of the form say 0 comma artificial problem would have the this artificial problem would have a basic feasible solution of the form of 00043, so to speak. So x1 x2 x3 going to 0, y1 y2 being 4 and 3. Okay, we first write down our matrix M which contains all the constraint coefficients as well as the right hand side. We also list down our variables x1 x2 x3 y1 y2 and basic variables as y1 y2, and I write it entirely in a table form with a header row and header column as well as a frame just to make it easily visible. So this is how it looks like. Cj minus fj basically refers to my original cost function, sorry, original function which I have to optimize, whereas cj minus zj refers to my artificial function, artificial cost function to be optimized. Now, as I mentioned uh, in the text where we are moving around variables y1 and y2, I changed my last row to reflect it. So if I that is basically minus 5x1 minus 4x2 minus 3x3 plus 7 equal to 0. So I basically move it around, take the 7 to the right hand side, make it minus 1, and this is how my problem looks like. Now I will be defining the pivoting function as well as the pivot column and pivot row functions that we have already seen in the class. Pivot column, pivot row tells me which column and which row to choose. Pivoting basically moves around the variables so that we can have one particular variable on the left hand side in place of another. Now if I just for a recap, I will list down my table again, and what do we see here? This is how the table looks like. I now wish to find out which column and which column and row entries to pivot. So that is being evaluated by the pivot column and the pivot row function. I run this. So it tells me that I have to take column index 1 and row index 0. So if I, sorry, column 1 and row 0. So minus 5 and 4 by 2, which is 2 having the largest ratio. So with this in mind, I will pivot the table, rewrite my basic variables based on whatever variables I have here. So my new basic variable second. So initially my basic variables are y1, y2. Now it will be y1, comma x1. If I just print it out, this is what the assignment does. And now I reprint the table. Okay, so this is how it looks like. Okay, there is a negative coefficient at minus 4 by 3. We'll be again looking through the pivot row, pivot column functions. So I basically get the column 0 and row 2. So for next one, that shouldn't change anything. Oh, sorry. It's x3 and 0 2. So it's actually y1 and x3. Sorry. I again use the pivot column, pivot row functions to determine where to move around. So 0, comma 2. So basically, I think y1 and x3 will be interchanged. If I run the pivoting and then add the correct basic variables, this is how it looks like. So now if I print out my new table, this is what it seems. So x3, x1 are now my basic variables. So this completes the phase 1. All of them are non-negative. X1, x2, x3 are all going to 0. Next, phase 2 will require only looking at the correct columns. So we'll be dropping all the artificial columns. So only x1, x2, x3 and the x1, x2, x3 and the right hand side RHS column will be retained. First three entries, so that will first three rows 0 to 3. So that will basically take us to my original problem. So this is how the original problem would look like. Okay, and to determine again which where pivoting action would take place, we use the pivot column, pivot row functions. So 1, comma 1. So which will be x1 and x2 being interchanged. If I run the pivoting, I basically my new basic variables are changed to x2 and x3. And this is how my column table looks like. Okay, so this is how it looks like. basic variables. So next to right hand side. Sorry, pivoting M1. Should be pivoting M1. Right, so this is how it looks like, and you can see that from this we get uh, the values for x3 and x2 to be 2 by 5 and 9 by 5 respectively as my optimal values. Okay, and my optimal solution is x2 is 2 by 5 and x3 is 9 by 5 with my optimal value turning out to be 11 by 5. If I solve this process using the inbuilt function, we have already seen how we write the matrices, equality constants, variable types, standard forms, optimal solution, and the optimal value turn out to be x2 is equal to 2 by 5, x3 is equal to 9 by 5, with the optimal value is 11 by 5. So x2 2 by 5, x3 9 by 5, and optimal value is 11 by 5. Okay, so this is one of the ways to solve uh, LPP, particularly useful when a starting basic feasible solution is not easily available. Split it into two problems, introduce artificial variables, introduce an artificial constraint, drive that artificial objective function, drive that artificial objective function to zero, and then use that to get a basic feasible solution for your original problem, then go back and solve it in the same method, simplex method that we have seen before. The next problem that I have is uses something called as the big M method, wherein suppose we have a linear program problem of the form z is equal to c transpose x with ax is equal to b. So we have to first write this in the standard form. But suppose we have ax is equal to b and x greater or equal to 0. Then we redefine the problem to be minimize z is equal to c transpose x plus m into summation ui, where ui refers to a vector of artificial variables and m is a large positive constant. This artificial variable helps us to obtain an initial basic solution, but it may cause violation of certain constraints. So we need to get rid of those before they appear in the optimal simplex table. So to achieve this will be for each artificial variable that we choose, a large penalty m into ui is added to the objective function. Okay. So the way we do this is we have to minimize z is equal to c transpose x or z is equal to minus 3x1 plus x2 plus x3 subjected to three constraints. One of them is two are inequality, one is equality. So we basically add appropriate slack variable in the first constraint and surplus variable in the second constraint to make it into make this into a convert it into standard form. Next, for the what we see here is that for the second and third constraints, um, there is no easy, readily available basic feasible solution. So two artificial uh, variables u1, u2 are introduced and added into the equation, and correspondingly two penalties mu1 and mu2 are added to the large posit are added to the objective function. And then the way we figure this out is we using the constant equations we determine u1 u2 in with respect to the other variables and then plug them back into my constant equation, sorry, objective function. So this creates an objective function which has this capital M as a variable. So we'll go through the steps together. first we specify the capital variable M. Next we specify the matrix A which contains coefficient of the constraints. So x1, x2, x3, x4, x5, u1, u2 as well as the right hand side. Okay, so this is how we'll write it down. Okay, with this in mind, we next write down our header as well as columns. So x1, x2, x3, x4, x5, u1, u2, right hand side, and the rows are basically my non-basic variables. So x4, u1 and u2. So no constraint ui was introduced in x4. So x4, u1, u2, and cj minus zj. Now we'll be looking at the entry which is the most negative. So clearly that is this entry minus 3m plus 1 corresponding to variable x3. So this is where we enter our equation, and we exit it at so it's either 11 by 1, 3 by 2 or 1 by 1. So we exit it at the ratio of the RHS by whatever positive entries we have wherever it is minimum. So that is U2 in this case. Enter through X3, exit through U2. So we'll be basically pivoting 2 comma 2. And my right hand side U2 will be appropriately replaced with X3. So this creates my new table. Again, here you can see that the largest negative entry is likely minus m plus 1. M, again, remember, is a very large number that we have not specified. And the way we now look at this is so we need to enter through x2, and our exit is on either 1 by 1, 10 by minus 2. 1 by 1 has the lowest positive ratio. So we'll be entering x2, leaving through u1. So pivot basically occurs around 1 comma 1 and replace u2 with x2 on the side. So my basic variables become x4, x3, x2 and x3 respectively. And yeah, so now the largest positive negative entry is minus 1. And if I take the ratio of RHS, minimum positive is the 12 by 3, so x1. So we'll be entering through x1 and exiting through x4, pivot around 0, 0. So this creates my matrix that looks like this. Okay, so from this we obtain x1, x2, x3 values as 4, 1 and 9, and the corresponding objective function to be minus 2. If I use the inbuilt function using the mixed integer linear program problem using the GLPK solver, I set my variable, set my objectives, write down my constraints, and finally show the problem. So it looks like, and if I solve it for the optimal value, I get the optimal value as minus 2 and the optimal solution is 419, which is exactly what we obtained here. So again, using the big M method, we have solved LPP, and yeah, this big M basically tries to combine the two phases in the two-phase simplex method into a single process. Okay. Yeah. Next problem we have, consider the problem where we maximize z is equal to 40x1 plus 25x2 plus 50x3 subject to the two inequality constraints below. We have to write the dual of this problem and check for its basic feasible solutions, as well as then find optimal solutions using the interactive LPP problem. So first we write down matrix A, which is 1, 5, 4, 2, 5, 4, and 1, 2, 3. Miss that here. 1, 2 and 3 less or equal to 45. Okay, so A is a 3 by 3 matrix containing constraint coefficients. B is 3 by 1 vector, right hand side of the constraints, and C is uh, object coefficients corresponding to the objective function. So we write down the interactive LPP problem using ABC. So next to X3, problem type is maxima of Z. Constraints are less or equal to for all three, and variable type are greater or equal to 0 for the two. I show P. This is how the problem looks like. Next, I find the dual of the LPP problem. So, what is basically duality? So, for each of these LPP problems, there exists another LPP problem, and the solution to the dual can be obtained through solution of the primary problem and vice versa. And sometimes it might be easier to solve the dual rather than the original problem, and as well as sometimes you get some additional insights. So suppose you are trying to solve a problem with z is equal to c transpose x, where ax greater or equal to b and x is greater or equal to 0. Then the dual of this is given as maximizing w is equal to b transpose y, wherein some a transpose y is less or equal to c and y is greater or equal to 0. So the cost vector C is basically in the primary problem is moved to the right hand side of the constraints in the dual, whereas the right hand side of the so this cost moves to right hand side of the dual constraints of dual, whereas the right hand side of the constraints of the primary moves to the cost of the dual. So this is a symmetric form of duality, and if I show the dual of P, you can see that the cost coefficients in the primal are now in the right hand side of the right hand side of the dual, whereas the right hand side of the primary problem are now in the cost coefficients of the dual. And the dual of the dual should again get us by the original problem, which is what we see. Optimal solution of P and its optimal values 30, 0, 0, 1200, and similarly optimal solution of the dual as well as its optimal value 0, 20, 0 and 1200. So okay, next we just print out whatever the objective coefficients are, and you can for both P and D, and you can see that they are basically the right hand side of the objective coefficient of primary and right hand side of the constants of the primary respectively. To find basic feasible solutions, we take again we use part of the code that we have already studied in the class. Basic feasible solution for Ax is equal to b, wherein we evaluate a small submatrix if with independent columns. From that, we evaluate M inverse b as my solution, and for if the basic solution requires all three coefficients to be non-negative, then it is considered a basic feasible solution. Otherwise, it is not considered a. Otherwise, since it violates the non-negative requirement of any solution that we have, feasible solution that we have, it is no longer a basic solution. So, if I look at my primary or primal question, so from this I obtain my A matrix, my B matrix. If I look at the basic feasible solution of A, I will see that the basic feasible solutions of A are basically there are 6 different basic feasible solutions coming out of from this, and from a possible 6C3, so that is how much 6C3 would be like 6, 5, or around 20, I think. Uh, so only six basic feasible solutions exist, and corresponding to those, I calculate my cost 10, 20, 11, 10, 12, 10, 180, 450, and 0. So which gives me, from this I can see that my objective is maximized at this particular corner point for like a higher dimensional polygon, and that is my solution. If I similarly calculate the basic feasible solution for the dual, again I write down the matrices A matrix B vector and calculate the basic feasible solution. I get only three possible basic feasible solutions, and these are the points corresponding to them. Okay, so this solves this particular question about duality of an LPP, dual of an LPP problem, primal dual, their basic feasible solution, optimal solutions, and its properties. If I now wish to, I've already used the interactive LPP problem to show the optimal values. Okay, so this is what I obtained as my solution for the above example. Next, problem number 8. Use the dual simplex method to solve the problem. Minimize z is equal to 5x1 plus 4x2 subjected to 4x1 plus 3x2 greater or equal to 10. 3x1 minus 5x2 greater or equal to 10. x1 x2 greater or equal to 0. So we first define my again my pivoting function, my dual pivot row and dual pivot column functions to to be used later in the code. So the first thing that we do here is the pivoting function. Again, like it updates the simplex table, nothing too fancy. Then dual pivot row basically finds out what my outgoing uh, variable is. Dual pivot column finds out my incoming variable. Okay, so we first define our A matrix, which is the coefficient of constraints, my B matrix, right hand side of the constraints. This is how it looks like. Next, I create the augmented matrix A augmented B. Next, I showcase this whole thing in the form of table with corresponding headers and columns. Sorry, corresponding column headers. This is how it looks like. Okay. Think I have x1, x2, x1, x2, x3, x4, and right hand side. Okay. So right hand side is don't know. Uh, okay, we'll check into that. Oh, I've already. Right. So this is my correct coefficient matrix for the constraints. Corresponding slack variables have been added. X3, x4. Similarly, the objective function is written in the third row. Next, I create the augmented matrix by combining this matrix with my right hand side vector. Now I write this whole thing in the table form. So you have x1, x2, x3, x4 right hand side, and basic variables as x3, x4, and then cj minus zj for the cost, uh, rather objective function. My number of basic variables is 2, so I use the dual pivot row function with two variables. It evaluates what my outgoing row is. and my outgoing variable is. Similarly, I use the dual pivot column to calculate my incoming variable from where I'm entering. So next I assign the correct basic variable. So it turns out, using the dual pivot row function, it turns out that my outgoing variable is x4, whereas my incoming variable is x1. So this and this. So again, like, you could look at the coefficients of Cj minus Zj, and then the coefficients of right hand side, ratio of right hand side to the entries in the column. So x4 comma x1 becomes my uh, outgoing and incoming variable respectively, which converts my basic variable from x3 x4 to x3 x1. If I pivot the augmented matrix around these variables, I get to be of the form like this. There is a mistake here. So my augmented matrix ends up looking like this after pivoting. And what does this tell me? This tells me that my objective function below is all positive. So no further. So this is what we obtain. So we basically see that my z, uh, my cost objective function has a value of 20 at x1 is equal to 4 and x3 is equal to 6. If I use the inbuilt function using the mixed integer linear program where I minimize using the GLPK solver, I set my objective function, I write down my constraints, and if I now solve this, I see that my optimal solution turns out to be 20 for x1 is equal to 4, x1 is equal to 4, and x2 is equal to 0. So x2, x4 are both 0 in this case. So this is how I solve my uh, solve use the dual simplex method to solve this particular problem. Okay, so this covers the set of problems I had for the day.